Hello again. In our last lecture, we introduced the notion of verifying or proving the correctness of a particular protocol, and we said that that was an important thing to do. And we introduced the notion also of belief logic, which is a modal logic for reasoning about these things. Let's look at a particular one called the band logic. This is one of the most widely used belief logics for reasoning about protocols. Okay, so what is band? Well, first of all, the name comes from the guys who invented this thing, which is Burroughs, Abadi, and Needham, B-A-N, and it's a modal logic of belief. In any logic, you've got a set of primitives for describing formulas, and then you've got a set of inference rules for inferring new facts from facts that you already have in your database, essentially. So there are a number of primitives in the band logic, or ways of building primitives, and here are a number of them listed. It's a fairly complicated logic, and I wouldn't expect anybody to memorize all this stuff, but let's go through a few of these. So for example, the first symbol up there is P believes X, meaning that P is entitled to act as if X is true. Since this is a belief logic, this is going to be a very important one, because what we would like to infer at the end of the day, for example, is that P believes that he shares a key with Q, that sort of thing. Okay, so A sees X means that A has received a message containing X. A once said K and A once said X means, well, where K is a key, that A used a key, and so we believe that A knows how to use that key and knows what the key is, and that A once said X means that we received a message that we believe came from A. A has jurisdiction over X. This is kind of an interesting one. What it means is that in this case, A is an authority over things of type X. So for example, if you think about Needham-Schroeder, there's a key server, and we believe that the key server is an authority about generating good keys for use as session keys. A and B share a key, K, means that they have it and presumably nobody else does except maybe some of their trusted friends. Okay, here's three more. X is fresh, meaning that we believe that X is new to the current run of the protocol. B has public key K, pretty obvious, and A and B share some secret X. Okay, so we use these primitives to build up formulas and then reason about the formulas using rules of inference. Let's look at those. Okay, here's an example of a rule of inference. And the idea here is to formalize patterns of inference that you might intuitively come to if you're just reasoning about a protocol. For example, this one says, this is called message meaning. It says if A believes that A and B share a key, i.e. only they share it, and A receives a message which is encrypted with that key, then A is entitled to believe that that message must have come from B, assuming that it didn't come from A. This actually formalizes a pattern of inference that we've used several times, and the idea now is we want to make our reasoning rigorous. Okay, here's a couple more. Nonce verification says if A believes that a message it receives is fresh, that is new to the current run of the protocol, and A believes that the message came from B, or that B said X, then A believes that B believes X. Now you see something kind of funny about this one. X in this case really isn't a message. It's most likely a statement of belief, and we'll see where those come from in a few minutes. The jurisdiction rule says the following. It says if A believes that B is an authority on things of type X, and A believes that B believes X, then A is entitled to believe X. This just formalizes the common sense rule that if I hear something from an expert in those matters, then I'm entitled to believe that. So I take his word for it. Okay, so here's a problem, right? Remember that a protocol really is a program. These A, B, S, whoever are sending around messages. And what we want to derive from that is a set of beliefs or statements about beliefs. Where do they come from? Well, there's a step that you have to go through which is called idealization. And the point of idealization is to stare at the statement of the protocol and try to figure out what it is that a particular message or transaction in the protocol is trying to accomplish in terms of making the receiver believe a certain thing. So for example, in Needham-Schroeder, the third message that was sent is displayed here. A sends to B, KAB encrypted with KBS. Well, somebody stared at this and they said, well, what's really going on there is A is trying to tell B that A and B now share that key, KAB. And by the way, that fact is encrypted with KBS to show that it must have come from S initially. Right. The idealization step is important to get from the sending of these messages to the belief, the state of the belief logic, but it's not easy to carry out, and it can be done ambiguously. And so for any particular message, you have to understand the protocol pretty well and make the leap of faith that you're doing this right. Okay, so what have we said today? Well, the band logic is one of these belief logics, and it's a widely used, a very important tool for reasoning about protocols. It's a modal logic with 10 primitives and a number of inference rules. And the idea now is you're supposed to use this logic to write down a series of initial beliefs and idealize the beliefs that you're supposed to get from the running of the protocol, and turn the crank and figure out whether you can actually prove that the protocol accomplishes its goals. We're going to look at that in our next lecture. Thank you.